Okay, so let's begin. So today we are going to talk about more modern and advanced diffusion models. And if we have time, we're going to talk about some architectures of doing fine tuning or like video diffusion models. But before that, let's talk about some more advanced techniques in diffusion models. We are focusing on Stable Diffusion 3. So first, we are talking about the techniques or like the architecture or the building blocks used by Stable Diffusion 3. It includes a lot of different papers and works that from many different researchers. So first of all, one of the interesting paper is EMU. There's also EMU 2 and other things, but we start from the original EMU. This is a result of the EMU. You can see that it is quite artistic and more like artworks, high quality things, because this is what these papers focusing on. They're trying to producing high quality images instead of something like more casual, more like photos that you taken from by using an iPhone or just a random group photos. They are more focusing on something more like artworks or like more professional quality images. So you can definitely see it from the examples here. So it outperforms like SDXL on visual appeal. So it is focused. You can see that it is focusing on visual appeal. It is not focusing on like fidelities or like varieties or different styles, or it is more focusing on visual appeal. The contribution of this paper is to provide a good fine-tuning recipe for aesthetic alignment to text-to-image models. So you can see that again, it is focusing on more like visual appealing things. It provides a recipe, which means it is trying a lot of different settings, and it present in the paper a working recipe that you can follow on. If you don't have enough like resource to try different method, or if you just want to stick with one successful workflow, then here the paper provide a detailed recipes to achieve high quality image models, to fine tuning a high quality image models. Okay, so it works. This recipe, this workflow works pretty well for most of the popular models architectures. So this, although it doesn't seems to be a lot, like a new architecture like transformers or like a new activations or like a new MLP, like a gated linear unit or something like that. It is not, but it provides a workflow, a recipe to actually help you to fine tuning the models, because when training stable diffusion models like stable diffusion 1.5 or stable diffusion 2, it requires a lot of high quality images, and it is not easy. Although we know that we have to do something to kind of filtering the data set to when you try to train a replicate of stable diffusion 1.5 or 1.4, there are publicly available data set that you can try to download. Most of this data set like CC, Google CC, conceptual caption. Also, when we try to training a data set, training a model for like a stable diffusion, like a text to image model, you need a data set. There are freely available, kind of freely available data set. One of the famous one is the CC data set, which is means CC does not mean Creative Commons. It means conceptual caption. So it contains a pair of image and a text, which is kind of like caption or prompt. So one of them is Google CC, and there are others. And for conceptual, like it has like 12 million subset, and it also has a 3 million subset called the CC3M. And this data set, you can download like 2.5 gigabytes. It doesn't seem too bad, right? But if you try to, this is only the image URL and the prompt. It only has a caption and the image URL. You can see that right, like here. It's separated by tab, which called the TSV, kind of like CSV. CSV is column separate, but this is a tab separated. So it contains each row contains, it contains image URL and caption. So it doesn't contain an image itself. You have to download the image by following this URL to download. And this download image may have copyrighted. So, and it may be missing, or because it is in this list, they maybe feel like, okay, a lot of people downloading it. So they kind of block the automatic download, like a car or like a robot. So it block automatic downloading. So it is likely you only like 60% or 70% of the image. You can only download like 60 or 70% of all these images. If you try multiple times, maybe the success rate will up to like 80%, but definitely not going to be 100%. So you can get the image file, the data set. The problem is the quality of this data set may not be that good. So one problem is that it has various resolution and various image qualities. Some of them are more artistic or like professional and high quality, and some of them might be just random random pictures, random photos taken by people, but it happens to have some caption. People have captioned it, and also the caption itself is going to have various different kind of quality. Some of them are very detailed descriptions. Some of them may be just a brief, like I think for this image is okay, but you can see that it definitely shorter sentences, and some of them may be even wrong. So you definitely need to have a data pipeline to filtering the thing. And there are various data sets you can get, but you need to do some filtering. A lot of people have already providing some subset of this data set that has better qualities. But anyway, emu paper provide recipes that might work. Okay, so another contribution to, so the detailed pipeline you should read into the paper. But another contribution for emu is Fourier transform, the Fourier field feature transform. So by pre-processing the RGB image by using the Fourier feature transform, if they're using this autoencoder, they are getting higher, and they are doing two different things. One is try to consider the channels of the autoencoder. So like Stable Diffusion, the autoencoder has four channels. Because after the autoencoder, you get a latent. It has a width and height, and also a channel. It has 4 channels. So they do some experiment to see how many channel is the best fit for, like in this text, the diffusion models. Their conclusion is that 16 channel is the best one. They have different settings, but 16 channels resulting the best, getting the best result in all these metrics. Like FID is lower is better because it is a distance. PSNR and SSIM is higher is better. SSIM has is up to 1, and the PSNR can get to infinity. But 34 is pretty good. And another contribution is just like I mentioned before, by using a Fourier feature transformer. Transform, not a transformer. It's using a Fourier feature transform for autoencoder. Instead of using RGB itself, it will get a slightly better result in SSIM, APSNR, FID. So they do have certain contribution, but I think the most important one is the channel one. So it gives you an idea of how many channels the latent, for the autoencoder, how many channel is the best one. So 16 seems to be better. But the thing is, like I probably mentioned before, for the fine-tuning, the autoencoder is usually not the issue. Usually not the issue. Except if you are more like trying to fine-tune the style or feeling or like a color. If you want to adjust the color, like being a little bit warmer or cooler, kind of like that things. If that is something that you are heading for, or you want to do, then autoencoder, you probably won't want to adjust autoencoder. But in most of the time, in that case, for example, if you want to just change the temperature of the color, you can also do it in like OpenCV or like in Photoshop. You can do that easily. And the more like stable way to do that. So that another way to achieve the similar effect by using like a filter in a sense that in like OpenCV or Photoshop. But in general, if that is not the purpose for adjusting, like if you want to fine tune the models to have a better object, to recognize a new object or like new character or like a new style, probably most likely the autoencoder is not the bottleneck or the things that block you. You probably just want to train the denoiser or like maybe the text encoder. So that you take whatever autoencoder you have. But in this case, in the case of Immune, they are trying to achieve better visual appealing. So they actually, I think that makes sense that autoencoder is something that does matter in this scenario. Okay, so here are some of the workflow for doing the data pipeline. First of all, they do an automatic filtering. Like I said, you need to read the paper in more detail, but here is some brief explanation of what it is. One thing is that automatic filtering, because they have a lot of images. They have just a lot of images. So they are using some algorithm to filter the images, like resolution or certain automatic filters to reduce the pool to from billions to a few hundred of millions. Still a lot, but much better than billions of images. Then they do the human filtering. So you need to pay people to do that. So it is a two-stage human filtering process. They want to return only highly aesthetic images, so that if we have a very only data set containing only highly aesthetic images, then we do the fine tuning. We are expecting the model to generate only high aesthetic style of images. That is the goal. So they do the two-stage of filtering. So why do we need two-stage? Or like if we including automatic filtering, we have three-stage. It is because we can use cheaper way to do a high quantity of images to filtering. Then we use when we reduce the number of images, then we can use a more high quality, which means more expensive filter. This filter including like auto algorithm or human. So in human filtering process, we have two stage. So you can imagine that the first stage is due by like the normal human, usual like an average human, and the second stage is due by specialist like expert. So that is in fact the case for the first stage. They just recruit annotators, but they train them to actually to filtering the image to select good image out from all this image. Then they get down to like 20,000 images. Then they actually to recruit specialists, maybe like a photographer or like professional artist who has a good understanding of the what is actually a image that has a good aesthetic test or style. So they following the good photographic principles like composition, lighting, color and contrast, subject and background, and additional subjective assessment. So they're really experts. But definitely these experts are more expensive than the average person. But we only have right now we only have like 20,000 images. So in this for this 20,000 images, they hire specialist annotators to filtering out a subset of the images that has highly aesthetic. So that's the line. So one thing you need to kind of focusing or like to notice is a number, because how many we all know that if you have if you have a large data set, it is good, but if you have a smaller data set that is high quality, that is also good. But how small? Even for a small data set, it should contains enough number of data. So you should notice on the how many not how many image are remaining in the data set, and you should look into the samples of this data, this image in different stages to check which one to actually feel the quality of it. So this will help you to build your common sense of the training of what kind of data set can produce what kind of models. So these are certain generated image by emu. although they are not entirely exactly photorealistic, but you can see that they are looking like more professional or feelings and more like compositions, lighting, and the color and contrast things are uh more appealing, more visually appealing. Okay, so emu. There's a following paper over emu, which is the uh, desolated emu. It only needs 3 steps, 1 step, 2 steps. I mean, a few steps to do that. So they do it by using a distillation. So they remain the same properties that has more aesthetic style or aesthetic images, high quality, more for professional qualities, but it doesn't require many steps to do the sampling. So this one is the following paper does. So you can check that it does a distillation to make the image generation faster. But we're going to talk about the LCM latent consistent model later, which is the way to go to do the distillation. We're going to more detail in LCM. And also, there's a DALI 3. So DALI is the original DALI 2, I think, original popular diffusion models that get very popularized this kind of thing, although it is not open source. So when the stable diffusion is released, it really get a very huge impact on general public. But I think a lot of people knowing this kind of text to the potential possibility of this text to image generated things back when the first DALI released. To be honest, when the first DALI, the original DALI released, I was kind of have certain doubt of how well it is. In fact, the DALI is not using. I think it is not using diffusion. The second one is the DALI 2 is, but the original one may not. So I mean, I definitely know that DALI has achieved something, but my kind of doubt is mostly about how what is the range or like the possibility it can generate. So for original DALI, it already can generate certain things like avocado chair, or like the original DALI, DALI 2. Okay, this is the original, the page of the original DALI. So this one is the iconic or like the things that people think about DALI can generate is the avocado chair. People remember this one by avocado chair, and it also have something like this guy, a baby daikon radish in a tutu walking a dog. You can use the text prompt to do certain things. So back then, people, I think, I have no doubt this model can generate this type of things, but I don't know what else it can generate. But by DALI 2, the doubtness is already gone because DALI 2, I mean, by that time, the diffusion model is more widely known and knowing. Okay, so people already know that. And this is the DALI 3. This paper has a lot of ideas to improving the image generation with better caption. So it is also a lot of things is focusing on how to build a better data set. The architecture wise is not that important. It is mostly on the data set things. Kind of like a scaling rule we talk about in large language model. The three things is important. The size of data set, the size of model, and the computation, the total computation power, the training. So that has three, but the model architecture is kind of secondary. So it's sort of applied to many of the different situations, like even with like diffusion models. So they are in this case they are also like an email that focusing more on the data set since. So the prompt following ability of text-to-image model can be substantially improved by training on highly descriptive generated image captions. So the first thing they observe is that, okay, so we can actually improve the ability of this text-to-image model for following our prompt correctly by training it on highly descriptive generated image caption. Also, caption is important. The caption, we should work on caption to have a more high quality captions. So, and also they observe that existing text-to-image models struggle to follow detailed image descriptions and often ignore words or confuse the meaning of prompts. So this is the things they are focusing on. Like the emu, they are more focusing on the pipeline things. But for emu, they are focusing on visual appealing. But here they are more focusing on prompt following, the ability to following the prompt. Okay, and then they also seems to find that there are a lot of noisy or inaccurate inaccurate image captions in the training data set, like we mentioned before. The prompt may have various qualities or even wrong captions. So they suspect that maybe if we clean up the data set to have a more high quality, to have a better quality of the captions, this may improve the prompt I mean, may improve the ability of the models to following the prompt more closely or correctly. So here is one example. So before DALL-E 3 or like maybe Stable Diffusion 3, it is quite amazing achievement for this generated image. You can see that this is an illustration from a graphic novel. So this is a style. It usually works pretty well. But you can see that a bustling city street under the shine of a full moon. So it actually has a full moon. And you can see the street. The sidewalk bustling with pedestrians enjoying the nightlife. You can see that it actually follows pretty well. At the corner store, a young woman with very red hair, dressed in a signature velvet cloak, is arguing with a grumpy old vendor. The grumpy old vendor, a tall, sophisticated man, is wearing a sharp suit, sports a noteworthy mustache, is animatedly conversing on his steampunk telephone. You can see that it actually follows the prompt perfectly. Every element in the prompt is existing is in the image, and also I mean, if you have experience in generative image, you may see that some early models like Stable Diffusion 1.4, 1.5 will mistakenly like if you tell it has a red hair and a black dress, it may has a red hair. It may generate an image that has a red hair and red dress, or black hair, black dress, because it has a difficulty to actually following the things to identify which object is belong to which one, which property should apply to which object. If you have multiple, especially if you have multiple people in the thing, in the image, like one person is wearing one person has a black hair, and one person has brown hair, and another person has a red hair, it may get confused. So this image perfectly illustrate the or like the ability what DALL-E 3 is special for, is designed for. So what they do is to do the dataset recaptioning. Although you may think that this is okay, this is just easy work. I mean, there's no creativity on it. You are just doing the hard work, and but the thing that we appreciated is that although this idea may not be too like too genius, too creative, but it requires a lot of resource and tries to make it perfect. So what we get from this report or paper is that it is an expensive result. So we can learn from this expensive result, which we are very difficult to replicate by ourselves, and we can get something from this expensive result. It's so difficult that is almost you cannot if you don't have enough resource or like a big team or a lot of like money, this is almost impossible to do that. There are something is possible to do is that you improve your like programming or coding abilities. This is difficult, but that is doable. This kind of things is almost unachievable if you don't have if by your own. I mean, at least by your own. So this is something we appreciated that they share their experience. So even though this might seems to be mainly like more like common sense or like okay, the easiest way to go. We know that it is not easy. You may not try success in first try, or even if you just do once, the result is still pretty expensive. I mean, the experience is pretty expensive. So what they do is that the important detail that are commonly omitted. So the presence of the object like the sinks in a kitchen or stop sign along sidewalk and descriptions of those objects. So these are usually, I mean, for the original data set, they are doing the caption by human labor. So they are hiring human to do to see the image and write the caption. So that's why the quality of this caption are vary. But the reason that they're using people to do that is originally this data set is used to train image captioner. The text to image models was not serious in back then. There were a lot of text to image models. Mostly are more like in a more restricted area, like generating flowers, generating birds, not like the models like the text-to-image model you see in nowadays, they're mostly for like a specific object. A more like serious things or like more practical things is image to text models, which is called image captioning. So the image captioning requires some data set. So originally there's no data set about it. So people are using like human annotators to do the labeling. So they see an image to write the caption. Sometimes they use like an ImageNet or other things like a category. Originally there's ImageNet. So ImageNet, every image has a category, like because they are doing the classification things, or like maybe some data set for doing the object detection things. So it is possible to generate some certain kind. If you have some template, or like if this is a object detection, I mean, this is a classification data set. So maybe we have a label. This image is a image of a dog. This is a cat. So you can actually generate the caption by a template. This is an image of a dog. This is an image. Oh, this is a photo of a cat. Kind of like this thing. This is possible, but they are more restricted because they have only certain template. So they still require some data set that has a real captioning. Those captioning are done by human annotators. But you can imagine that when a people writing a description of an image, they may have something that is usually overlooked or ignored or kind of doesn't really care. For example, the object like a sinks in a kitchen, because this is not important. We kind of assume that there's a sink in the kitchen, or stop sign along the sidewalk and description of this object. Probably they are just saying, okay, this is street or this is a kitchen. People is standing in a kitchen, kind of things like that. They're not going to describe most of the details. Imagine you are annotators. You are paying by something like how many images you have done the caption. You probably will not going to write like a 1,000-word article about this one image. You probably just write one or two brief sentence to describe this image. And this is probably what we need for a image captioning dataset, training dataset. So, but for text to image, they can observe that they lack of certain details, descriptions on some more insignificant object, and also like the position of the object in the scene and the number of those objects. Also, like which one is on the left or which one is on the right. If we have an object detection dataset, these things we may have the pretty much the accurate position, location of each object. But for image captioning, they all usually lack of this kind of thing. So the common sense details like the color and the size of the object in a sense, for some reason, and the text that is displayed in an image. This one is also important because a lot of time when we generate an image, like from text to generate an image, we want to have some text on the image. Maybe it is a comic strip, so people are saying something in the dialogue, or maybe we want to have a sign of a store or a sign or some text on your T-shirt. If the description doesn't have this information, then we are not be able to actually has a very good image generative model to generate correct text. So that's why images are not good to generate even for the modern models. it is not good to very good to generate text in like Chinese or Japanese, but they are pretty good to generate English text, especially for the modern models. Let me check. Okay. Okay. Um. Okay. So how do we fix it? So maybe for the object, you can imagine a few solutions. These are the situations or possible potential problems. So what are solutions? So for the object, the location of object, maybe we can use some object detection method to get the location of each object, so we can do it automatically. Maybe we can also do using algorithm or other things to find the color or the size of the object. And maybe we can use image captioning models to get more information on this image, and maybe we can use large language model to kind of refresh or to organize all the information we got in these things. For a text, maybe you can use an OCR to actually find the text in the images, and maybe we can replace the text. If we find where the text is, we can actually kind of replace the text. They are probably not doing this thing, but imagine some potential solution to this one. We can replace the text to arbitrary text in certain case. So here are the possibility, and this is what they do. So for example, you can see that for this image, in the data set, they actually originally they have a very short description, like pretty much like now at victoriapumping.co.uk. So probably this is automatically gathered information. Okay, so I forgot to mention something, that a lot of captions in the data set, so some may be generated by algorithm by using a data set like object detection or like a classification data set. Some are by human labor, and some of them are by, because we are crawling using crawler to get image from the internet. So usually the image is contained in a web page. It has a text description of its image, or maybe you can use the text around this image to automatically get a caption. So usually this caption may be kind of weird. For example, you can see that now at victorianplumbering.com .uk. So this is definitely a pretty poor quality caption. And you can imagine that it maybe exists in web page. And this one is just totally weird. As he finished just about, I don't know where it comes from, but this is happening in the text original data set, and this one is just a bunch of number, and we can do the short descriptions, short captions right here. You can see that a white modern bath tube sit on the wooden floor. This is, at least is correct. It is short, but it is correct. And a quilt with an iron on it, and a jar of rhubarb liquid sitting on a paper background. And also, like it mentioned before, we can consider a more detailed caption that describe every detail, like the small things, like a secondary things or location or size of everything. So you can see that it has a very detailed. It could have it can have a very detailed description. Okay. So here is they are using some automated captioner and large language like we said before. I kind of forget the detail of it, so you may check in the dataset. But for an image captioner, one of the image captioner is using this COCA, the contrastive captioner things, which is I think it is. Oh yeah, we can see that it is by Google, so you can use this one to build a, a, a better image text foundation model. So these are more like you can see that multi-model language models. So because when we're doing this kind of things, we need more kind of like what I said is using maybe like a YOLO, like a segment anything model, like image captioner. But currently the best image captioner may be a multi-model large language model. So here are certain multi-model large language model. You can see that this one is this size is built in last year. So currently it may be different. You can see that the Gemini Cloud GPT, this one is very close. It's it's actually pretty good to comparing to like the lowest human possibly available. So there is like you can check this website to see different that the leaderboard result of leaderboard of like the things. So the leaderboard you see on the slide is the leaderboard last year. So this one is done by last year. You can see that even the best one like Gemini Ultra is still considerably worse than the human expert. We can just see the overall. Okay. Let me. Okay. In certain area like human social science, like the health and medicine, but in general, it is overall it is significantly worse than even the worst human expert. However, this is the updated leaderboard this year. You can see that O3 is actually there are a lot of models surpass the human expert low, or even surpass the median one. That O3 Gemini 2.5 Pro, like O4 Mini, O1, or even Grok 3 Beta. And if for the open source model, you can see that these are open source model. Some of the open source model is better than the best closed source model last year. You can see that the Skywork, or maybe like Llama 4, Maverick, we are expecting that maybe Llama for Behemoth is going to be open source, but currently it is not. But the Maverick is open source and it is pretty good. And the Skywork R1v2 can achieve pretty good result. Okay, then and also you can see that a lot of models are above like 70%, 70. Okay, like internal VL, like QVQ. But if you're using like O3 or like Gemini Pro 2.5 Pro, they are very close to the median of human expert, or even surpass them. So by using this model and the human, you can use them to actually to um to build a better so you have a lot of tools to build a better captioning. We haven't talked about how to train or doing multi-model large language model. So that is also topics we are going to talk about. There are many different ways, and there are also contains. Consist of a lot of different ways to actually building a data set from various different sources, and building the like a question and answer, and those kind of things. They are involving using object detection data, object detection data set, or like a classification data set, or things like that. Okay. Another thing we want to talk about is flow matching. We probably already, I forget, did we talk about the flow this year? Probably not. So there's a thing called the flow. Flow model, like continuous normalizing flow, and it also has relationship to the neural ordinary differential equation. But we can probably skip them. We're going to talk about the flow matching for generative modeling. So it can be considered as a variation of a diffusion model. That is something we call the flow matching. A lot of modern models are actually using flow matching instead of using the original diffusion process. So we have a probability density path in consider, which is a time-dependent probability density function. Kind of like a flow sense like here. And we can also have a time-dependent vector field, consider as a vector field, but it depends on time. So the flow matching is considering in these settings, but with a lot of different, they are using a continuous normalizing flow, like what we do for normalizing flow. They start from the normalizing flow root. Let me go back to the flow things. So basically, a flow is something that you have both direction. By we are from one distribution, like this one, that is the non-distribution, to we are trained like a target distribution. This is called target distribution. Then we are trying to find a pathway from like a morphic from one distribution to another. 所以 flow 它基本上做的事情是我们想要，我们现在有两个 distribution， 一个是 target distribution， 一个是那个算是就是 白噪音那种通常是白噪音吧。看 ，so we can basically see the non-distribution as white noise. Generally, they are just using white noise. For this case, this is white noise in one dimension. So it's just normal distribution, one-dimensional or normal distribution. But in general, you can consider we are starting from a multi-dimensional Gaussian distribution. So this is a non-one, the original one, which we can generate like a noise, like we use in diffusion models. So the flow models is in general doing the same similar things, like finding a pathway from this guy to this guy. This is from the data. So how do we actually find these like smooth pathway from one distribution to another? That is the question. Usually we are trying to use some mathematic function, object, or mathematical tools to derive things like this one. 好，所以这个基本上就是我们就是反正就是有两个 distribution， 那我们把它用数学上的方式把它看成是一个像是向量场一样的东西，把它从这边然后变过去。So in technically, we are trying to find a way. I mean, for a flow model, are trying to find a way that is kind of like you can use the neural network, but it has two directions. It has two directions. One from I mean, forward from the white noise to the target, and the other is from target to the white noise. And we construct our model in a way so that it is reversible. So we train it only one way, and automatically get the other way. So one one thing that we would do is to use the ordinary differential equation. So that is one way to achieve this result. So we consider these things like a vector field, like a differential equation, or like a differential equation. So we know the start and the end. The differential equation has certain parameters that is unknown, but it can be decided by using a neural network, sort of like a denoising neural network things. So that is how the normalizing flow does. So the continuous means that is introduced in this the continuous normalizing flow is introduced in this paper because they are using the ODE to make the time to be continuous. Okay, so the flow metric is feel the similar things by using the continuous normalizing flow, but they are using it to interpret the diffusion process. They get a new formula, similar but a little bit different formula that to the original formula of a diffusion model. Recall that in a diffusion model we have two different approach. One is from the like a stochastic Markov process things to do a denoise, and the other one is to from the stochastic differential equation thing. And here is trying to do the similar things, but using the reversible things like here. So for the flow, it always using things that can be reversible. So the neural ODE solves the equation via differential ODE solvers. However, it is pretty computational expensive. Okay, originally, we are using a neural ODE solver to do the continuous normalizing flow. This is the original idea presented in this paper. But in this one, they argue that the ODE is kind of expensive. So they are trying to use a more efficient alternative. That is regress a vector field and then generate a probability path. That is their approach. They're still trying to think about the continuous normalizing flow, but they are not trying. They are not using the neural ODE to solve it. They're using another way to do that. So they are trying to control a path. Okay, let's say a conditionally probability path. So you can see something resemble to the kind of similar to the diffusion things. So this might be, I mean, this definitely inspired by the diffusion models to solve the things, but they see things in the framework of continuous normalizing flow. So they use similar things to solve it. They get a marginal vector field to generate the things, and finally, after certain computation, they get a flow matching objective. If you really look into it, it is kind of like what happened to the stochastic differential equation approach. I mean, a score function. We call it a score function approach, and also kind of like the denoising approach. We finally get something like a mean square error. So finally, we get something like a mean square error. So no matter which foundation you start from, you get something like a denoising autoencoder. But that is also an interesting part to actually do it. So I actually put certain important part of formula in it, but I am not going to go into too detail about it. I'm just going to give you a brief picture because the details last year, but I probably give a more detailed discussion of these things. But I think it is okay to get a rough idea. So it starts from the continuous normalizing flow and following certain, but instead of using new ODE because it is too expensive, so they kind of mimic what since doing the diffusion model, they develop certain mathematical tools to solve the problem, and then finally they get a objective called the flow matching objective. So it is sort of like this one, and in fact, it is also since kind of like a mean square error, and you get something like there are certain subtle detail differences, but basically you get something very similar to what you can see in the diffusion model. Okay, so they are also doing the conditional flow matching, which is kind of like what we wish to do, like a text prompting, like text condition or image condition. So they are using a different framework to or like approach to construct something similar to what the diffusion model does, but because it has a different theoretic foundation, so you can build things in a different way, like how the condition work. Okay, so it can use this to derive how the condition should just work. So this is the conditional flow matching objective. They are doing like this one. So combining when they apply to the diffusion, kind of using diffusion model, this is the actual formula like this one. So combining a diffusion condition VF with flow matching objective offers attractive training alternative. So they find there's all similar like what we do for the Markov processing, like the score function thing. Also similar in this case, they start from something from theoretic, but eventually they have to do some experiment to see whether this approach or these interpretations has a practical benefits. So in this case, they do some experiment and find that this is more stable and robust in the experiments. Also, the score function, like a score matching approach, it was the more popular idea of like, because it is easier. Like we introduced back then when we introducing a score matching things. We start from introducing like a DDPM, like a denoising Markov processing, and we introducing the score matching approaches. And the best thing about score matching approach is it is has a very good explanation of why the noise is needed. But currently, flow matching is the most popular approach in modern models. So most of the models are using flow matching, including like the Stable Diffusion 3. So they are using flow matching thing. So there are only some certain like subtle differences, because basically they are still using something like a mean square error. But because of the foundation is different, they have a slightly different variations and formula recipe about the things. So they found that this modified recipe is better, and they have an interesting mathematical foundation. Okay, so they have a different condition, like a optimal transport condition. Of this is another things. They have experience on some toy example like this one. They found that the path, because like we probably mentioned, they are trying to find certain paths for like the optimal transport path. You get something like this one directly from one place to another. But for the diffusion one, the trajectory is more like curvature, because the optimal transport is trying to find a way to from one state to another in a more economic or like efficient way to do that. So this is not surprise. It is at least in certain representation, you can see that it is in a straight line, which represent more efficient way of movement. So here are more like a toy example. We do a lot of toy. In back then, when we have a homework about the flow, normalizing flow, we used to have a homework about normalizing flow that is using a neural ODE method to solve it. So there are a lot of standard toy example. This is one of them, which is called the chessboard pattern. So we are always starting from a Gaussian distribution, and we are trying to move this one to this one. So I mean, this is a target like a chessboard. So you can see that in this toy example, if we apply different approach like a score matching or flow matching with diffusion, like condition, and the flow matching with optimal transport, you can see that in this type of toy example, you can see the differences and see what is fundamentally different. You can see that above two are pretty much similar. No matter you are using whether you are using a score matching or flow matching, they are pretty similar. Probably even better for score matching. Like, I mean, in this case, they are certainly sort of kind of you think you can see some like small spots or squares because eventually it's going to be a squares. You can see something like in here, but this one is so condensed. It still looks like just one thing. However, if you are using a form matching with the optimal transport condition, you can see that in the middle of it, it is already becomes more like a chessboard pattern, even though it is only in the midway. But for a score matching or like diffusion things like form matching or like score matching, even at like 30% of a press, it still kind of look like a kind of a mass, a crowd instead of kind of things like a chessboard. So that's the difference. You can compare to this graph because they come from a more straightforward path. If you are using diffusion, it's more like the path or the trajectory is more like a curve. It's not so direct, but if you are using optimal transport, it is very straightforward to it. So it will get something more like this one than this one. So here are a few other examples. So you can see that eventually, no matter what you are using, score matching diffusion, from matching diffusion, or from matching optimal transport, if you run enough steps, you will still get the chessboard pattern. But the from matching with optimal transport may be more efficient or fast to converge to what we to the target to the target. So that is a benefit, more stable and more efficient. So here are some metrics about the proper the quality of the things. Like they are trying only on small data set, low resolution things, like ImageNet, 32 by 32, 64 by 64, or like CIFAR 10, which only contain like 50,000 images of a resolution 32 by 32. But you can see that in these things, they are like in a negative log likelihood, FID or NFE, they are getting better result for the setting of from matching with optimal transport. Here is another example of showing the image directly using the score matching with diffusion or from matching with optimal transport. So you can only see a slightly different. It converts more reasonably comparing to using the score matching because it's getting still very noisy in the halfway, but by using the from matching, you can kind of see the things in appears in a more linear way. That's the differences between from matching and the score matching. Okay, so here is the state the used by using transformers instead of using like the unit attention unit. So here is an approach to replace the denoiser with a transformer. They are not using a attention unit, they are using a transformer instead. The denoise image transformer is in short, you write as a DIT. DIT. So they are considered the diffusion transformer, like DITS, DITB, DITL, DITXL. This is the FID. I consider the FID. So their best model is DIT. FID is lower is better. So their base model is DIT XL2, G right here, which you can see that it is kind of like this one. So originally, the Stable Diffusion is using attention unit, but in modern models, people are using DIT or different kind of DIT, but they are using transformer. So originally, what is a unit? What is a attention unit? It looks like this one. So this is from the paper. Attention unit, learning where to look for the pancreas. So it is kind of like a unit, but there is an attention. You can see that there is an attention gate in each of layer. So that is attention unit. It is not a transformer. So it is not a transformer. But for DIT, that is a diffusion image transformer. They are using a transformer. So each of the DIT block, you can see that it has a multi-head attention right here. It has a feed-forward network right here, just like other transformer block. So this one is kind of like other transformer block. So you have layer normalization. You do the scale shift that is we have a gamma and the beta one to do a shift. This is for mostly for the conditioning. The conditioning is by using the scale or scale shift right before and after the multi-head attention. So that is the design of the DIT. So the middle part here is the standard transformer. The only different thing about DIT is that it has a conditioning from MLP by using like a gamma 1 and beta 1. So this is a standard design of the DIT block. So you have like a transformer, you can have multiple DIT block. After that, you will have a layer normalization and the linear reshape and get a noise and the sigma. The input is like noise latent and doing the H5 so that it can be as input of the DIT block. And also you have a conditioning like a time step T and Y. I recall that in the noise block, we have a noise image, which is here, noise latent, because we are usually consider in a latent space. So we have a noise latent, but we still have two more input. One is the time step, and the other is the condition, the real condition, like a prompt, text prompt. Okay, so here they go from here. So they get it from embedding and get this become the conditioning in each of them and doing things right here. So the conditioning is applying to the transformer block by using a scale, shift, and the scale. Okay, and the petrify is we just need to suppose we have a image like 128 by 128. We does not use each of the pixel as a token. We use a small patch like a 8 by 8 patch. So if this is 100 by 128 by 128, and each patch is 8 by 8, 128 divided by 8 is 16. So we have a 16 by 16 tokens. So which is like a 256 tokens. Also, that is what we do for page 5 things. For This one is standard for like doing transformer on image. So this is called the image transformer. Like VIT, visual transformer. Yeah, vision transformer. That was a diffusion transformer, diffusion transformer DIT, and this is vision transformer VIT. So the petrified sense is start from the paper, famous paper. An image is worth 16 by 16 words. So this one is one of the famous paper about the vision transformer by applying the transformer on image. There were a lot of attention on how to apply transformer on image, including which we may introduce that the VQ-GAN paper. The paper name is, the title of the paper is the taming the transformer on like a image things. So that's, for example, they are using transformer to generate the latent. There were a lot of attempts on using transformers on image, but they are not that successful. I mean, usually we are not talking about the image generative model. We are talking about like object detection, classification, or like semantic segmentation, those kind of tasks. Back then, the CNN is still dominated, and transformer is not that performing not that well. So it's beginning with the vision transformer. The VIT is one of the approach that actually work. So the idea is pretty simple. They use a patch and position embedding. Basically, position embedding is necessary. So the only thing that is the only handling that is need to be choice and significant is the petrify. So instead of considering each pixel as a token, kind of like what we do in the VQ-GAN, because it is a low resolution, so that would kind of work. But in this case, they are using a petrify method to do the handling. So instead of doing pixel by pixel, they're doing it patch by patch, and they have a standard handling to do the petrify, petrify, petrification or petrify. Okay, and so it including the like a position embedding or patch, like this one. So this is a standard transformer encoder, like a transformer. They're using transformer encoder, but you can do it in decoder or in anything that is also works, because you can use encoder. The encoder, like we mentioned before, the difference between encoder and decoder is just the mask. Whether or not you want to mask to the mask the future. If you want to mask the future, kind of like an autoregressive thing, then it is a decoder. If you don't, everything can see everything, then it is an encoder. Except if you are combining encoder and decoder together, then it will have become the original architecture of the encoder decoder style of the transformer. But basically, if you are consider only the encoder and the decoder, the only thing different is the mask. But you can see that it has normalization, multi-head attention, and plus normalization, MLT feed-forward network. Again, you can replace it by like the gated unit things. Like we probably mentioned before, that is one of the choice. Or maybe you can use a mixture of expert. Right here, it also works. But basically, we call it feed-forward network, and the original is using MLP. Back then, probably there are not many choices. They are still using MLP. But again, like we said, you can use any options you want. But this one is called VIT. The only difference, the key point is the pagification. And they also find that no matter what image it is, 16 by 16 is the golden setting. But remember that this setting is mostly for like classification things. So comparing to the DIT block and the transformer block, they are pretty much the same, except in the DIT block, it has a condition. It has a mechanism to inject the condition into this transformer block. Other than that, they are identical. There are slightly differences, like we are specifying using layer normalization right here, and here just say normalization. But this does not matter much because the original transformer is using layer normalization, and we know that it can use the a square root, divided by square root that can use the normalization used by Llama. We have introduced that in the Llama architecture. They are using a different normalization, like a square root normalization things. But other than that, they are identical. The only difference is that they are using this guy to inject the condition into each block. So there are some variations. I'm not sure why this is getting more light. Probably I didn't set it correct, but anyway, by injecting the only issue or not the thing that we want to do is the goal is to injecting conditioning. There are other choices to do the injection. So one way to do that is to do the you can inject a condition in the multi-head cross attention. You can do that. First, you do a multi-head self attention, and you add a new block like a multi-head cross attention. You put a condition here to do this kind of thing. That is doable, and it is similar to the decoding part of the original transformer. But this is from the encoder. I mean, this condition is from encoder. So this one is definitely reasonable. And another choice for injecting condition is, okay, we're injecting just by simply concat the condition into the input tokens, kind of like the VQ GAN does, because the prompt and the image are concat together. So this one is another apparent choice, but the default DIT is using this architecture. But anyway, these two are also kind of apparent options that you may want to try, like in context conditioning or cross attention. So that is also some popular choice. It doesn't make sense to add them together, kind of like what we do for the control net or T2I adapter, because they don't have necessary to have the similar dimension. But if the condition is an image, your condition is an image, probably this is also a choice to simply add the image to this guy like the T2I adapter does. Also, the important thing that I mentioned here is just that there are always some options. There are always some apparent options. You have to aware in order to actually read the important part of this paper. So the important part is they choose this option. This is not the only option because we have something in mind that this, and if you have image, they can add them together. These are all options, but they choose this one. So that is something you can read from paper. 所以这边我想强调的重点就还是一样，就是你要知道哪一些东西是可能性的，就是你的可能性有哪一些，你才可以比较容易读懂它。因为这几个都是这 paper 也有列出来，这是他们就不过就是表示他们有想过了，他不是就是想不到其他方案才用这个，而是正常的话你都会想到这些正常方案，然后你正常的去实做它。不过他们最后选的就是这个东西，就是因为有实做过，他们觉得那个是最好的。但这都正常的，就是你用 cross attention，就像我们说那个 IP adapter 嘛，上次讲到 IP adapter 也是用 cross attention，然后这边用的是那个，而且那个attention unit 它也是 cross attention，那另外就是直接 concat 进去，因为都是 token 嘛 ，concat 进去，这是个方案。然后说相加的就像 T2 adapter，这些都是常见可以放进去的地方，也可以综合，就是说你可以大量的好几个不同的塞进去，但它是选择题，而不是一个，它就是比较像是一个选择题啦，就是你看你选的哪个方向，这样会比较容易理解它，也记住它。Okay, another thing is called the rectified flow transformer for a high resolution image synthesis. This is even simpler. It's still like a flow matching, but it is even simpler. They are simply connect the data to the noise in a straight line. So like we say, they have different paths, like what we see, like the optimal transport path, like the diffusion path. They're considered in a, because obviously there are different paths to from like white noise to the target distribution. There are different noise, but you only need to find the best one. But you have to design how to judge which one is the best. So they have a diffusion one and an optimal transport one. But in this, like the rectified flow, they're trying to think about, okay, we think the easiest one. We think about the path just to be this straight line, kind of like a straight line. They have some parameter like ATBT. You can do different things, like A0 is 1, B0 is 0, or A1 is 0, B1 is 1. This is the case that kind of like a different interpretation. You still have a different type of AT and BT, but you start from like X0. I mean, in the forward noising path, you start from X0, and you end up get to the epsilon. And for denoising path from 1 to 0, you start from epsilon, like a white noise, and get back to the X0. This is the probability path chosen by here. They are using a flow matching context. I mean, from flow matching framework, but they are only considering a straight line. So they can do the conditional flow matching, like the loss function, the target here. They compute with the straight line path. So they get their result. So their formula, finally get their formula right here. So still, I mean, you still got a denoising, mean square error denoising, and you with a different distribution. That the only difference you can see everything is the distribution and probably the weight. So they get a different weight and different things, but still get the mean square denoising. You can see that is noise, and this is denoising things. pretty easy. But they are kind of like the what do I do with for the conditional for matching things, but they are considering the straight line path directly. So this is a rectified for matching. There are some variants, like a rectified flow. So you have a different WT. You can choose different WT. They are also called EDM. So they are choosing different the WT in this case. They are choosing different one. You can see that this is rectified flow, like RF1 in this paper. They are using this one is similar. The T they add up together to be one. This is ATBT we see before, but their WTRF is 1 minus T, T over 1 minus T. And the other one is a little bit more complicated. It looks like this one, and they're using a EDM, WEDM, which is a more complicated weighted. And there's also a cosine things. It is more like this is also like an ATBT thing, and they use cosine instead of like more like a straight line here, like a more linear one like there. They use cosine and sine, and their WT their weighting is the hyperbolic second. So there are different variations on different things on different paper. There are also LDM linear since they use a modification of DDPM schedule to do that. So this is also another they call it LDM. So you can see that in this framework you can see a lot of different things in the same framework. So DDPM can be considered like this one. Okay. So they are okay here. Okay, so this is a rectify. They do some. So they based on their mathematical foundations. They have different. You can see that in different variations. And okay. So they also considering cosine scheduler and different scheduler. So their model, okay. So they are using rectify flow matching, and they are also modified their architecture. So by using the rectify flow matching framework, they can consider different settings in previous papers in a same framework. So they have slightly different like weighting and like alpha beta ATBT and the different weighting, so they can put them in a same framework. And also the architecture is different. So this is more like this is stable diffusion 3 architecture. Or this is a stable diffusion 3 architecture. So what the difference is they are using a modified DIT blocks. So these are DIT blocks, but they are taking more conditions. So like DIT blocks, the important part is how the condition is passing through the models. So first of all, the caption has going through different clips, and these conditions are using different way to in fact inject into or to pass through the DIT block. before that, let's talk about why we need to have this more complicated way to do the encoding. The reason is they want to have a more sophisticated or more modern or better quality text encoder. So basically, they are using a T5 XXL. So you can see that modern models are using T5 as a text encoder a lot. Originally, like a Stable Diffusion 1.4, 1.5, they are using Clip, some version of Clip at least. But recent models, you can see that if you download models to use it in like Comfy UI, you see that it use T5 a lot. So the rationale is to use a more sophisticated models like a larger clip and T5 XXL so that it can produce better text. They are hoping that by using this approach, they can produce like a more correct word on the image, in the image, like in a banner or like in a T-shirt, the text writing on a T-shirt things. But spoiler alert that in fact, even without this T5 XXL, the model still performs pretty well on the text generated on the image, on the generated image. But they claim that it is slightly better. So they have done something right other than the T5 XXL to make this model handling the text better. So in the like Stable Diffusion or other, even with Imagine 2 or so, if you want to generate a banner and use English, they probably will spell it wrong. But in later model, the spell is pretty good in the generative image. Okay, so the reason that is they want to inject more text information with more models. So they have 3 different encoder, including a clip G, clip L, and T5 XXL. Some of them are going to here through this pathway, and another of them are going to another part, more like the original, DIT. So this one is the original DIT part, like the scale things. But another way is more like concat things. Basically, they are like 2 transformers block, and some of them are putting together. So this DIT block is like original DIT, but they take 2 sequence of tokens together. One is from the text, and one is from the noise image latent, right here, like petrifying things, position in. This is like the VIT things. They take 2 input, and so this is why it's called MMDIT. So this is a detail of the MMDIT. So it has a two parallel transformer block, and they kind of have some cross attention to each other. So for this one, it is a transformer for the text prompt, for a text captioning from here to here. So you can see this is a linear part. This is the original like a layer normalization part. So this one is also for the other like a latent image, noise latent image. So they put them together to a attention part. They output 2 things. So they do kind of doing attention together, and they have 2 different separate output. So one is for the captioning, and one is for the latent, the denoise latent. Also, that's the difference between the original DIT. And also, the condition here is applying to both of these paths. So you can see that the scale things right here, scale and the shift things right here. This is the scale things, scale and the shift things, and also apply to the right hand side, right hand path here. The scale and the shift, scale, scale and the shift. So this is the architecture of the MMDIT that is used on Stable Diffusion 3. So the reason why this is designed in this way is because they want to inject more things about the text prompt. They want handling the text in a more dedicated or like more sophisticated way to do that. So originally they are, I mean, if you only pass through some simple thing, you only rely on the text encoder, and then you and the learned linear transformer to linear projector to project the latent into something like a scalar. But they want the text part to be more involved, to be more computated. So instead of just using it, they have a transformer to further process the text caption. But they also kept the original condition since the DIT condition. They keep it the same way, but they just add more things like we want to handle the text caption by more like transformer block. Okay, and they want the caption and the image to like interact more, so they put attention right here, the joint attention of the text information and the latent, which is the image information together. But only this part is joined part. After this part, they output two different output. One is for the layer. I mean, one is for the caption and one is for latent. So they separate their way. So this one is a reasonable and a simple choice. Are there other options? They certainly have other options. They could do attention separately, the self attention separately, and do a cross attention right here. That's the apparent way. But this one seems to be a pretty reasonable and simple choice. I think separate the attention to be like self attention, and the cross attention. It's probably the other reasonable, the most reasonable option than this one. But this one seems to be okay and seems to work. So people, if we want to modify the architecture, maybe the other architecture, like I said, like self attention, and cross attention to here and the cross attention to here. Maybe that is the other apparent option, but this one is the architecture people use. Okay, so see the example. They're using ImageNet and the CC 12 million. The conceptual caption dataset we talk about. Sometimes we use multiple of dataset, but in this case they are using only like at least two dataset, and they are training a lot of different formulation on these two dataset. There are 61 different formulation because they have seen. You can see that they have considered a lot of different formula recipes. That each training requires a huge amount of computational power, but they seems to have more than enough. So computational power. So they not only do the one training, they do a 61 training and find out which one is the best. So I kind of believe that this architecture may be better than the one that I described before. Probably they have already tried it before. Both of them seems reasonable, but I mean, they definitely chose this one. Okay, so they consider a lot of different ways, like the if laws, like optional or free prediction laws. We have when we see the code last week, when we see the code, you can see that there are two options, like optional or free prediction. Like is you predict the optional or you predict the other part, the latent part. And of course, there are also if laws with this guy, and the if laws with this guys, if laws with this guy, and the EDM laws, scheduling with that. So they try a lot of different recipes, and for each round they are using EMA weights, which stands for exponential moving average, which is a standard way to increase the quality of training and make the final produced model more stable. And they are using like clip store and FID, the virtual image distance. This is another. These are all popular metrics on the determine the quality of images. I probably should still add this part back because I was kind of FID was a part in the game. When we in the previous semester we discussed FID and other metrics with the game, but probably I should make this one as an independent part. So we probably will talk about what FID and clip score later in later lectures. Okay, so this was just saying they try a lot of different combinations and find the best one. So here is the result. So like we said, this paper are very precious because they are doing some experiments that you are unable to do that. You may find, like I did, I cannot emphasize it more. You may find like what you do is difficult, like modify code, doing experiment, doing fine tuning is difficult. But just remember, this kind of things is much more difficult. It's more difficult in like 2 or 3 magnitude than what you are doing right here. Maybe I shouldn't say the magnitude because they are kind of impossible for you to do that by yourself. But what you are doing, no matter how difficult it is, they are achievable by yourself, by one person, by writing code, by doing experiment, by using a computer that is available in your lab or maybe in the cloud. But this scale of experiment is so huge that it requires a huge team, a large team with a large resource available to you. Okay, but as you can see that, okay, they're using rank average. So smaller is better. They're ranking them by like 1, 2, 3, 4. Top one, the best one, the second one, the third one, and then they rank them. So you can see that the best one is RF with log normalization. So this one is the formula. Probably the above several is the like 5 steps, 50 steps, depends on how many steps you want. But the above one, it seems to be better formula recipes. So if you want to do a diffusion style, like a rectified from metric model, these are the best bet that you can have if you want to start with something. And also they try to see the clip score and the FID on ImageNet and CC12 medium. The FID is smaller, the better, and the clip score is large, the better. So you can see that the rectified flow is significantly better approach. The best one is they are putting like this one, but all of this rectified flow has some certain thing that performance better. And also, rectified flow are sample efficient, so it performs better than other formulation when sampling fewer steps. So which means it makes the inference or like the generation faster. But even with more steps, the RF logarithm does not perform worse than other models, but it performs better when we have smaller steps. Okay, another paper is using it's called the improved autoencoder. Kind of like what we see in the email. It says that 16 channel is better. So I mean, in the stable diffusion 3, they are also choosing d equals to 16, like we see it in the email paper. So they are also changing the auto retrain and have a new autoencoder that has 16 channels. So again, PSNR is greater the better. If you recall that when we see the email, it is like 34, so which is much better than this one. But they are not comparable because they are applying this metric on different data sets. So they are not. But you can see that 34, 30 something is really good. It's a really good score for PSNR. And for SSIM, it is like 68%. For the perceptual similarity, perhaps like LPIPs or other things. The similarity, although it called the similarity, it is smaller is better. So you can see that. And FID, because it's distant, it's definitely smaller better. So they confirm the result in email so that the latent, the autoencoder with latent 16 is better than 4-channel or 8-channel autoencoder. They are also using the caption, like we say in email and in like DALI 3. They are improved caption, mostly like what they DALI 3 does. They are also doing improved captioning things similar to what DALI 3 does. So it is getting better. They are using like Coq VLM to improve the text to image to improve the caption. And another thing is, like we said, they improve the text to image backbone, like the architecture. So they're comparing the things with all text encoder and without T5. This is probably a little bit smaller, but if you look into here, even without T5, this one, I mean, the important part is coffee. You can still see COFFE inside the image. And this one is scaling transformer model is awesome. It, as far as I can see, it is spelled correctly for each word. For this one, maybe a little bit. This one may not be as good as this one, but still pretty good. So the thing is, they observe that T5 to be important for complex prompts. This is their observation. So if the prompt is so complicated, then T5 is necessary. If it is longer, if shorter, then it is still pretty much the same. So if longer, for longer prompt, the T5 is important for the quality of things. But you can judge by yourself. I think they're pretty close to each other. This one is more significant, but they are pretty close to. And even without T5, maybe you can generate multiple times. You can get a similar result. But they definitely still have differences, which is very apparent, observable differences. Okay, so they also do a lot of data pre-processing, like pre-training, mitigation, and pre-computing image and text embedding to speed up the training. And they also do the QK normalization, positional encoding for varying aspect ratio. Also, this is they do a lot of detailed things. So they consider how to do the positional encoding for different aspect ratio. And they also do the resolution dependent shifting of time step scheduling. So other than this, I mean, the major improvement, they do a lot of small improvement right here. So just list a few of the small improvement. So the resulting model is quite good. So stable diffusion 3 is actually quite good model. Although currently people may use high dream or like Flux or high dream is more considered to be better and generate higher quality, but still diffusion 3 is still quite amazing achievement, and they use a lot of different experiments and data to generate things. Okay, so here are some images that generated by the Stable Diffusion 3. 好，所以这边我们大概简单介绍 Stable Diffusion 3它的那个内容。哦，so we are this concludes our introduction to the Stable Diffusion 3 and discussion to the Stable Diffusion 3. You can see that although the original idea of diffusion model is quite straightforward, like they contain a lot of mathematics formulas, which I intentionally skip in this lecture. But there are still a lot of room for improvement, both in technical details like we see in the architecture right here, like a MMDIT, MMDIT, or in the data processing part, like how to make a better quality data set, mostly for prompting or selecting better pictures, better images, and for the mathematical foundations. So even though like score matching is quite amazing, but there's other interpretations which is considered to be superior, like rectify formation. They are using a framework to consider multiple of different I mean a lot of different previous results, and from that foundation they can, I mean, the rectify formation, they can derive certain formulas easily, and trying out all these type of formulas, and they can select the best one. So that's what they were doing. So I hope that this introduction helps you to to have some idea of what is a potential improvement on an existing technology, which is already amazing. I mean, the original like latent diffusion model is already amazing, but you can still imagine the potential way to improve it in data pre-processing, although it may seems to be less attractive, less creative, or that kind of easy, but that is important for quality. And also, if you are more interested in technical details, it is possible to combine more models, modern models together. Like in this case, it combines T5 XXL inside the model. But you or like a DIT, it uses transformer instead of using the attention unit. But if you recall this type of thing, you can see that what is necessary to get right here. First of all, you need to already know that VIT is important. VIT is one of a big achievement because people, like I said, people try to use transformer on images. There are a lot of attempts on trying transformer on image, and they are not that successful. They are not that successful. So VIT is the first one that is pretty successful. And this is one is a famous paper. So if you suppose you don't know VIT, it is very difficult. I mean, you probably will not design a DIT because DIT is for a specific issue. It is using VIT to to solve with a specific issue. That is, we need to inject the condition inside, and it actually tried several, I mean, 3 different apparent approach, like the scale things, like the concave things, like cross attention things. And I mean, all these 3 kind of things is require some background knowledge. All these 3 things are not novel. They are not novel. They are apparent, but they were novel. For example, the scale shifter things can have a root to the like ADA-in, adaptive instant normalization, and to like style gain to like modular modulation, or kind of like the modulation. So they are existing technology. They are similar to like a feature map modulation, kind of like modulation. But after back then, they are kind of I mean, if you are trying to add that in, this is kind of by using ADA is for like style transfer. The history about ADA in is it is used for style transfer by using adaptive instant normalization. This is the original paper for ADA-in, and it used some kind of instant normalization with scaling. So that can be considered kind of novel, especially they are trying to solve a problem for like style transformation, style transfer. What is style transfer? It is kind of popular back in 2017. You give an image like this one and the style, you combine them together to apply this style on this image. So this is called the style transfer, and ADA make it faster, much faster. Originally, there another way to do the style transfer, which is quite slow. But okay, ADA is here. So, but after that, I mean, in nowadays, this type of, I mean, like this type of method is just okay. You are using this way. This is not novel. It's just one of the apparent option to inject the input, condition input inside. And this way has an advantage that is kind of separate things together. You can apply it to, as a plugin, and it apply to the whole things. Kind of like attention, cross attention thing. It apply to the whole image. Not just if we use addition like the control net or a T2I adapter, they are positionally dependent. But this type are applying to everything. But this is just a sense that people in their toolbox already. It is a standard tool in the toolbox since 2017. It's not special. Like concatenating, this is just concatenating, okay. We have a new name in context conditioning, okay. But this is not novel. This is just a tool in your toolbox. And by using cross attention, again, after the transformer, attention is all you need. The transformer is introduced. This is just a regular method for doing things. But even though it is not so technically, creatively novel, but if they are not in your toolbox, you are unable to do this type of modification. Also, you need to see more things and have more tools in your toolbox. Okay, so this is the technical part. Also, there is a things right here. Like it starts from pretty straightforward idea. Like we want a more advanced text encoder. Like we probably mentioned right here. Improve text to image backbone, like it here. But in order to achieve it, you need to do something. I think this architecture is kind of novel, but if you want to design something, it is probably the way that you go. You probably would think about removing this part by using this part. But this is more like a cross attention. It's actually similar to cross attention things. Like I said, you have a self attention, then a cross attention, but this one is going through another pipeline of the transformer block, and they do this in both direction. You can do that. So that is an apparent design. Well, I think either design should work. You probably can think about several similar design and do some adjustment, choose one of the best. But this thing is necessary. It is not so novel. A little bit novel. Like I said, this is their design. It is for first proposed in this paper. So definitely they get a credit. But is this design so novel, so something that people cannot think of these things without this paper? No, this is not. I think people will reproduce similar architecture if they want to solve a similar problem. They will design similar architecture. This is something achievable. Okay, so I think this one is a pretty good example of showing a various of research in a context of developing a high quality image generator. And the Stable Diffusion 3, like I said, is not even considered to be the best image generator now. So maybe even not the best generator last year. Because Flux has definitely getting much better. Okay, I will get a very quick because I talked it yesterday about, so I can get a really quick summarize on okay, here it should work. Or present right here. Okay, so let me also introduce update to a more modern situation of the image generative model. So the first one is the trend is going through diffusion models, dedicated image generative model to or video generative model to a multi-model model. Like everything has been integrated into a multi-model large language model, kind of like a Gemini or ChatGPT. So this one is an image generated by ChatGPT. I got a like a cartoon strip, comic strip right here, and I generate this one by using a ChatGPT prompt, simply called a create image and transform it to a real person style, and it actually generates the things quite faithfully. There are small glitches like this cup is disappeared, magically disappeared from here, and maybe this one is more like a dark brown things, but clearly you can see that it is kind of like water. So yeah, there are some small glitches, but I would say this is 90% good. So this is ChatGPT does. So this is probably the future of image generative models, and probably already this is the image generative model today. Another example, you can see that this is another meme comic strip, and it can generate very good, including the text, everything. So these two are generated by ChatGPT, but ChatGPT is not. It is the future, and currently it probably already generates the best quality images already. But there's still something not there yet. For one example, this is another similar things. It has April, May, or other things. But you can see that in here, the problem is ChatGPT generate they put a cup. They didn't spill the coffee right here. The coffee is right directly into the cup, which kind of reduce the effect of what the image shows. So this is what Gemini do. I put this image into Gemini. I have tried a lot of times by using ChatGPT, using different prompts, ask it to focus on the coffee should not go into a cup, by using Mandarin Chinese to write a prompt. Use a lot of different ways to do that. It does not work. So I use a Gemini image editing feature to put this image to Gemini and ask it to it edit the image. So it does the work here to, this one seems to be pretty good enough. I probably will want her hand to be a little bit higher, like this one, but I think it's good enough. The thing is, you can see the earphone, the earbud here, the cord is not connected to the phone, and it still has a cord. Originally, it should be okay, but it is not there. And again, I asked Gemini to do that a lot of different way. It never did. It cannot do both. To do the 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 cord things connect to the phone and the coffee spill out on the table in a better way. But you can see that the benefit of using large model to do the image editing is you can do more in a more interactive way, in a more natural user interface. So this is done using Google AI Studio. And also, Google provide Field 2. If you're using Google AI Studio, this is a prompt that I was testing on like a video generating model that is a dog jump through a fire ring and turn into a firebird. So this is generated by Field 2, which is okay, which is quite okay. Probably I mean the direction of the dog is changed unnaturally, but I believe if I try it a little bit, a few times, and adjusting the prompt a little bit, it will generate pretty good result. This is another. I'm using Gemini. The previous one is using AI Studio, Google AI Studio, and the other one is using Gemini. Gemini also has a model called Field 2. You can use that to generate image, which is also okay. It's not perfect, but it is actually much better than other models. So I believe if I try to adjust it a little bit, it will get a better result. So what I mean is this is generated by Sora. Sora is probably number 2 or still one of the first tier video generative models. But you can see that Sora does not generate this prompt. I mean, it's not as good as what the Field 2 does. And this one is already the best one. I have tried like 10 times, do 10 different adjustments. Some of them even generate 2 images, I mean 2 videos at one time. They didn't do a lot of good job. This one is already the best one. But Sora can do a lot of different things, like they can make the video to be a loop, and you can have a storyboard to generate, to extend an image, to extend a video. So it has its benefit. But I think like image generation in the future, people are going to integrate everything into a language model. But right now, because video model is still pretty large, people are not. I don't think it will integrate into a language model anytime soon, but it definitely will. So here is one of the benchmark for video generation. This is called the Video Generation Arena Leaderboard. You can see that Google Field 2 is on the top, with a significant gap to the second one, which is Clean. And the third one is OpenAI Sora. These are already the best models available today. And but those are property models that crowdsource. You cannot run it on your local machine. For your local machine, the best model is 2.1, and the Hunyuan video, and March 1 video. These three are, although March 1 has been around for quite a while. Originally, it is definitely the top 1 open source model. But right now, I mean, after that, a lot of different model has come published, open source. So, but still, it stands pretty well against other newer models. And there are also like the previous one is text to video leaderboard, and this one is image to video leaderboard. In this leaderboard, the Clean comes to the top, and the Field 2 is a close second. And Sora, it seems does not perform that well on this leaderboard. It is right behind the Runway. You can see that Runway does not doing very well on this leaderboard. Although it has a quite amazing result, there are also like a Llama machine dream, Llama dream machine in this list, but it is far behind it, so you cannot see right here. But here, you can see that there are not many models in this leaderboard. Hunyuan is the open source one, and the one is also the open source one. The Alibaba 2.1 open source one. So they are probably, although you can see that is in the bottom, the Hunyuan video is on the bottom, but it is still pretty close to Sora. And Sora is not bad. Sora is not bad. It's just there are not many models in this list. So someone has to win, someone has to lose. And I think all of these models are pretty good. So this is the current situation of what the video generative models that you can have. Here is the image generative model, the same like Arena but for image generative model. As you can see that GPT-4o is currently the #1 model. It is not a diffusion model. Like, I mean, it may has used some diffusion technique inside, but it is not like a flux or like a stable diffusion model that is a pure diffusion model. But you can see that it is a #1 model as for now. And for an open source model, you can see like HW5 is pretty high, even better than the Imagine 3 version 2 of Google. Okay, and again, all these models are, if you see Arena, it is kind of like, it always produce 2 results and ask human judge. Like you can participate if you want. They will be showing you 2 images or 2 videos. You're going to choose which one is better. There's also for language model. There's Arena for large language model. As you can see, currently the best model like Flux, like HW5 are probably the best open source models available. But as you can see that GPT-4o stands on top. Defeat all things like a Mid-Journey or other models. So that's pretty interesting because already GPT-4o is on the top of image generative list. So I always, like I said, I always use Comfy UI to do all this type of thing. This one is for like Hunyuan video, my workflow for Hunyuan video. I designed this workflow. This is for LoRa, and this is for fast video, which is a distillation model to make things faster, kind of like the rectify, like the distillation models we talked before. And this is the same prop, like a dog jump through a fire ring and become a phoenix or become a fire bird. This is the same model by using the Hunyuan or one model. So they did pretty well for a dog jump over a ring, but the dog has never become. I mean, I can see it try to fly in this video, but it is not a bird at all. But again, if you see that okay, if you see that even the Sora does not do that well, so it seems to be quite okay. Okay, and here is another HW5, HW5. There are several ways to use this HW5. I mean, using Comfy UI is one way to do that. But there are simple way to actually try this model, like using Hugging Face Space, or even easier, if you are just using a text-to-image generation task, I mean, if you go to this model page and type the prompt like a dog jump through a fire ring and transform into a firebird, and press compute, you generate the image. And if you press the field code right here, you can actually see how to actually call the function. Like you are writing a Python code, it is in Python, and it's calling the API and will generating this image. So pretty easy to do that. So this is Hive Dream, and you can actually try it on Hugging Face. But when trying to instead of using instead of using Comfy UI, why want to try it really quick for generating an image, and my Comfy UI is not online yet because I usually host my Comfy UI on Colab by running a notebook and using Cloudflare to access to that machine. I can do that because I'm paid for the subscription. I think the user agreement is that if you are not paying it, you probably shouldn't do that. But I was paying it, so I've read the user agreement thoroughly, so I know that I can actually running the Comfy UI on the machine, on the Colab machine. So if you are not allowed to do that and you want to try an image generative model really quick, you can use diffuse craft on Hugging Face space. I probably have already introduced this before. And as I probably mentioned before, it includes a lot of functionality like ControlNet, T2I adapter, IP adapter, and you can actually run it in Docker because although it's running on zero, Hugging Face 0, and you can run the things on a machine, on a A100 machine. It is on an A100 machine, which actually you can have free usage on it. But the thing is, it is written in the code that it has some limitation of the computation time for each run. So if it is too long, it will pass the time limit. So it will not return the result. So even if you only have like a 4090, it is still pretty good to run it in Docker. And a lot of most of model, you can run most of the model to generate very high resolution images. If you want to run on on Hugging Face and using zero space, I'm pretty sure if you can do that, if you are paid to use a subscription, you have subscription. I'm not entirely sure you can host a zero space without subscription. I'm not entirely sure, but maybe you can because they are promoted to be freezing. If you want, you can fork this project to your own Hugging Face repo and change the code because there's a limitation on how long it can run. You can change it to the longest time. I believe it would be like 2 or 5 minutes. You can do that, and that will run pretty well. But you have a free usage limit on zero machine on yourself because everybody has a usage limit, and it is based on IP. So even if you have multiple accounts, it has a really complicated way to do the things. So I believe that even if you have multiple accounts, but you are using the same IP, the limitation might be applied or accumulate sum up to, and you have to wait for a cooldown. It has a cooldown mechanism to allow you to have a free quota to use it. So this one is something I recommended, but there are a lot of alternatives on Hugging Face. This may not be the best one already, but the thing is it contains a lot of different models that you can choose to play with. It takes some time. Usually it will be much, like you can have a different text, like text to image, image to image, impending, different control net, yeah, different type of control net, and you can choose different models like Stable Diffusion XL or Flux. These are actually fine-tuned Flux to actually generate any Japanese anime images, and their original Flux. A lot of different models like you can choose from, and you can actually use different LoRa. It contains a lot of different LoRa's you can choose to make it to generate different style things. Control net, IP adapter, phase resolution, styles. It has a style prompt, and other setting I haven't choose it before. Okay, so these are like classify free guidance rescale things. So it can do a lot of different things. It can also do something like doing the impending mask or doing upscaler or other preprocessor things like depth, canny, depth, open pose. So it is quite, I think it's quite well written. I mean, for the usability, that it pretty much just using a diffuser to load everything, but it organized everything quite well. So this is thing that I would use, but I think there are definitely other alternatives that maybe, I mean, maybe you think it's better, then that's fine. But you can choose one of them to use and try a lot of different model. And Civit AI contains a lot of different LoRa's and workflow of Comfy UI that you can find. But the things I want to introduce is the current status of the video generative models. The top video generative model right now, open source 1. You can see that it's 2.1. And it has a developing, progressively increasing ecosystem. Probably not entirely ecosystem, but it has a community already. So the original model has been evolved and improved. So currently it supports like text to video, image to video, and also first frame and the last frame to video. So for an image video, you provide an image that works as the first frame, and it can generate video according. Let's start with this image, but the also you can also has a text prompt. You can always has a text prompt, but the interesting part is FLF to video. It means you can provide the first frame, the image of the first frame, and the image of the last frame of this video, and you can generate a video from frame A, image A to image B. So that's pretty amazing. You can actually do like some kind of like interesting like interpolation of two segments of videos, or you can do something like concat a few videos together by using this method, by using the last frame of the previous video, previous segment of video as the first frame of the next segment, and so on. You generate a pretty good sequence of video. So this is official models provided by the one, but it has some community fine-tune or customized model. The first one is Phantom. So this is pretty doable, and similar things is doing to the image model, but this one's for a video. So the thing is that as you can see in this illustration, if you have one scenes, two scenes, three scenes together, I mean this guy can generate this video, and this like a rope, you can generate this video. Even better, if you have two things image as a reference, you can generate video contains these two, one people and one object. You can even have three people as a reference and generate one video contain these three people. And you can also have a combination of character, your background scene, the place, location, and the dress all together to generate a video. So this is called a phantom. Basically, this is also a video generative model, but with condition. I mean, you have a lot of different conditions. So you have to inject these images into the 2.1 model, so that model can take new input condition. And of course, you need to do some fine tuning. So, like I said, when we see the architecture of some of the image models, you can imagine that we can do similar things to. Although we haven't introduced the video generative models, which we will, but we haven't do that yet. But you can imagine this is similar. You do the regular options to this model to do the modification so that you can inject image condition into it, kind of like control net. But this is for image net, like T2I adapter. You can do that, or maybe IP adapter. But this is for image, for video. Another model is called Uni Animate DIT. The DIT is because one use DIT, so they are actually use one. But again, you do something modification so to help this model to take more conditional input, like a reference pose to this image, and a driving pose, a driving pose. So this is kind of like a video, but only for pose. Okay, I haven't put a link. Maybe link is right here. No. Okay, you can search this one and to go to there. So it does not only animate the like a animation or cartoon thing. It can animate a real human. Even if it cannot, you can fine tune this model to make it better. So you can see that the one itself is not modified. It's not trained. It's frozen. It's frozen, and the decoder is frozen. The only thing that they are training is the pulse encoder and the reference code encoder. So they are using a one encoder to do everything. And there are also other models like 2.1 font style model. This is not official from the one video. This is for community generated thing, but they have impending model and kind of like control net models. So all of these things require certain techniques to, and they are not too difficult, but and they have some difficulty. You definitely will encounter some difficulty and issues you need to solve to overcome, definitely. But I mean, training a model like one is so difficult that is almost unachievable. And this is some techniques that you can obtain and train yourself to actually doable. So this is something doable, and they are doing by experts. I'm pretty sure they are specialists and experts, and you can become an expert too, because this is something that's doable. So here are some models generated things in the by using these models. There are also like Hunyuan video. It also before one has been released, Hunyuan video was the top open source model by a huge leap. And so Hunyuan video also has some community, like Skyreel's V1 is a fine-tuned Hunyuan video by specified by using the human object, so it can generate better video for people. in it. Skyreal itself is quite interesting. It released a lot of different video models. Like a model can generate infinitely length film generative model, which worth to see. And it also has a Skyreal A2 that compose anything into video. I'm not sure these two models are based on, but they are quite interesting. A2 model is kind of like the Phantom model we see before. They can compose different input things into a video. Another interesting video model is LTX video. The interesting part is that it is real time. The quality is not so good, but I mean, at least if you are using it with a short prompt, it can generate some kind of garbage. But with a more detailed prompt, it can generate comparatively good videos comparative to, I mean, to one or 混元, or at least in some case. The prompt following ability may not be that great, and the video quality is a little bit worse than the 混元 or one, but it is real time. It generates high resolution video in very fast time. So it definitely, and it is continuous the development in continuous development. They released the version 0.9.6 just in last month. Another model video generative model worth to trying is the FramePack, which is released pretty much, I don't know, maybe in last 2 weeks. Okay, so this is also worth trying. Okay, so that's it for this lecture. So we introduced the field diffusion 3 techniques and architectures, and also we updated certain models for generated videos. Okay, so that's for over today. So for next week, we are going to talk more about the multi-model large language model. So how can we use large language model like GPT-4 to generate image? Probably we're not going to that, but we can use that. At least we can talk about other multi-model models so that to modify these models so that it can understand, can read images. Okay, so see you next week.